Class. Now we'll take up today valence bond theory for coordination complexes. There are two theories for coordination complexes. First is valence bond theory, but some limitations are there for valence bond theory. So crystal field theory also came into existence, but we will be studying valence bond theory first. So there are around 7 theories. I am reading one by one. Understand it. Every central metal atom CMA, every central metal atom makes available empty orbitals to accept lone pair from ligands. Class, I have already told you during for coordination complexes, central metal atom accepts lone pair from ligands. So it's saying the same thing. Every CMA makes available empty orbitals to accept lone pair from ligands, because we know that in one orbital 2 electrons can be accommodated. So that's why for one lone pair, one orbital is made available. Point number 2, number of empty orbitals is always equal to number of lone pair accepted. So if I am accepting 4, the element is accepting 4 lone pairs, then 4 empty orbitals will be available. If it is accepting 6 lone pairs, so 6 will be made available. During lone pair donation, these ligands occupy a fixed position in space. Their position around central metal atom is fixed in space, therefore hence they have fixed geometry and shape. So their geometry and shape are always fixed. Point number 4, empty orbitals of CMA hybridize to give rise to degenerate orbitals. Class, this word hybridize we have been studying from class 11. What happens? Mixing up of orbitals takes place to give rise to degenerate orbitals. Degenerate orbitals means same energy level. For coordination number 6, coordination number 6 means the CMA is accepting 6 lone pairs. There can be 2 hybridization, either sp3d2 hybridization or d2sp3 hybridization. For coordination number 4, if 4 lone pairs are being accepted, there can be 2 hybridization, either sp3, the structure will be tetrahedral, or dsp2, structure will be square planar. In this coordination number 6, either sp3d2 or d2sp3 both have same shape, that is octahedral. How they are going for sp3, how they are going for d2sp3, in due course of time in lectures you will understand. Point number 5, there are certain strong ligands. Remember class, there are certain strong ligands which pairs up unpaired electrons forcefully. If unpaired electrons are present in the valence orbital of central metal atom, then these ligands if present, they will forcefully pair up unpaired electrons. And such ligands are CO, that is your carbonyl, CN, cyano, and ammonia. Then we come to next, number 6. If ND orbitals are available for hybridization, they are called outer orbital complex. And if n-1d orbitals are available, they are called inner orbital complex, where n equals to principal quantum number of valence shell. Class, this point you will be understanding when I will be taking examples of valence bond theory. So for the timing, we'll just hold on. Point number 6, if ND orbitals are available, they are called outer orbital. If n-1d are available, they are called inner orbital complex. If after bond formation unpaired electrons are present, then the complex is called paramagnetic. Class, we have been studying in class 11 onwards. Whenever a substance has unpaired electrons, they are called paramagnetic. And once the substance is paramagnetic, complex is paramagnetic, it is going to be colored. And if all electrons are paired up, then complex is called diamagnetic, and it is always colorless. So class, please remember, if unpaired electrons are present after the bond has been formed, they are called paramagnetic and the complex becomes colored. And if all the electrons are paired up, the complex becomes colorless. This was your valence bond theory for coordination complexes. Now class, we are going to take examples of valence bond theory. Now class, we are going to take 2 examples here. Fe(H2O6Cl3). Here water is acting as a weak ligand, as I have told you, only 3 are there, CO, CN and ammonia. And in this case, we have taken strong ligand, CN. So we will do one by one. So let us focus here. Class, iron, atomic number is 26. Valence shell configuration is 3d6 4s2. Let us find out the oxidation number of iron here. Water has no charge, Cl has minus 3 charge. So whatever the charge plus 3, it is from iron only. So X is iron is plus 3 here. So class, we all know that 4s electrons are liberated first. So 3 electrons have been liberated. 2 will go from here, 1 will go from here. So the ultimate configuration becomes 3d5. So I have drawn 3d here with 5 electrons. 1, 2, 3, 4, 5. And now the very crucial step, class. How many legions are approaching? 6. And we cannot fill lone pair in it because it is already occupied by 1 electron and you cannot fill in an orbital more than 2. So if I take lone pair, it will be 3, so it will be ridiculous. So the lone pair will be only accepted in empty orbitals. So how many empty orbitals to be made by iron? 6, because it is going to accept 6 lone pairs. So class, 3D half filled cannot be filled, so it will move forward. See, after 3D we get 4s, after 4s we get 4p, after 4p we get 4d. In 4s it is getting 1 orbital, in 4p it is getting 3 orbitals, and in 4d it is getting 2 orbitals. So that will complete by 6. 1, 2, 3, 4, 5, 6. So what are those orbitals being involved? S, how many p? 3, and how many d? 2. So that's why I have written here sp3d2. It means that iron goes for sp3d2 hybridization. In the next step, I will make it the same energy level. So these are 5 orbitals, 1, 2, 3, 4, 5, half filled, and 6 orbitals which were involved in hybridization to accept lone pair. You see 1, 2, 3, 4, 5, 6. So now they will come in the same energy level because now they are the degenerate orbitals. 5 unpaired electrons initially, followed by 6 lone pair. 1, 2, 3, 4, 5, 6. So total 11 orbitals have been made here. So the hybridization sp3d2 shape, you all know it is our octahedral. How to draw the structure? Make an octahedral diagram, put iron in the middle, and 1, 2, 3, 4, and 5 and 6. So 6 lone pairs are surrounding iron in the space. Then class, we find 5 unpaired electrons over here. So it is paramagnetic behavior, and we all know that if the complex is paramagnetic, it will be always colored, and it will be called outer orbital complex. Class, listen very carefully. What is the principal quantum number of valence shell? Principal quantum number of valence shell is 4. So if 4d orbitals are being taken for the complex formation, remember class, ND means 4d. If 4d orbitals are taken for complex formation, we will call it outer orbital complex. If 3d would have been taken, n minus 1d would have been taken, then we will call it inner orbital complex. But in this case, since 4d orbital is involved in hybridization, therefore it is called outer orbital complex. So class, this is all regarding cell and feature of Fe(H2O6Cl3) called hexa aqua iron 3 chloride as per valence bond theory. So what was this weak ligand? So now we have taken another case where we have taken cyanide, and we all know that cyano is a strong ligand. First of all, break it. It gives me 4K positive plus, if it is 4 positive, it will be having 4 negative charge here. So FeCNO6 4 negative. Iron, let oxidation number of iron is X. Cyanide minus 1 into 6 will give you minus 6. This must be equal to minus 4. Solve it, we get X value plus 2. So oxidation number of iron is plus 2. So iron 26, configuration 3d6 4s2. 2 electrons liberated, it will be moving from 4s. So giving me 3d6. So I'll draw, as I have drawn here, 3d. So I have drawn 3d here. And in 3D we are getting 6 electrons as per Nernst rule. We'll fill up 1, 2, 3, 4, 5, and this is 6. So class, what do we find? We find still 4 unpaired electrons. Now we'll see our legend. What is the legend? Legend is very strong legend. What does it do? It makes forceful pairing of electrons. So cyanide, Cn is strong legend, therefore forceful pairing will take place. So ultimately these 4 unpaired electrons will be paired up forcefully. And class, we know for pairing 2 electrons are required. 4 electrons are there, so 2 pair will be formed. So first pair initially, and now this 4 electrons will be forcefully paired by cyanide. And how many cyanide is approaching? 6. 6 lone pair will be accepted. So 6 lone pair is accepted. We want 6 empty orbitals. Class, in 3D we are getting 2 here. Here we didn't get. That's why we moved forward and we got our outer orbital complex. But in this case, 3D is being involved in the hybridization. That's why it is inner orbital complex. So understand it very carefully. I repeat again, in this case 4D was taken, that's why it was outer orbital complex, but in this case due to forceful pairing, 2 orbitals in 3D levels are still vacant, that's why we'll call it inner orbital complex. So 6 lesions are approaching, only 2 empty orbitals are there, so now we'll look for 4s and 4p. Class, by moving to 4p, it has already got 6 orbitals here, 1, 2, 3, 4, 5, 6. So 6 orbitals this and 3 orbitals, 9 orbitals will be hybridized, getting to give you degenerate orbitals, means same energy level. So initial stage, initial 3 paired electrons, and now 6 empty orbitals where the lone pair has been accepted. 1, 2, 3, 4, 5, and 6. Sino. Now as write the salient feature as we have written over here. Salient feature hybridization is G2sp3. Shape is octahedral. Structure I have drawn here. K4 I will put outside the square bracket. Fe in the middle of the octahedral. 1, 2, 3, 4, 5, and 6 regions are there surrounding it. So structure is octahedral. Class, all electrons paired up, therefore diametric. Colorless, if the complex is diametric, it will be always colorless. And class, since 3D orbital has been involved here, remember the last point of valence bond theory, if n minus 1D orbitals are available for the bond formation, then we'll call it inner orbital complex, and the complex is inner orbital. Very, very important. Now class, we'll take up one more example. NiCO whole 4. So coordination number is here 4. Class, Ni, we know it is 28. Configuration is 3D8, 4s2. Class, CO has no charge on it, so Ni also has no charge on it, so Ni is 0 state here, so 3D8 4s2 is valid. Now let us do one thing here. 1, 2, 3, 4, 5 and 4s, 3D, 4s. Now let us fill up the electron as per the energy level to 1, 2, 3, 4, 5, 6, 7, 8 and 4s as 2 electrons. So it is the ground state configuration of nickel. Why ground state? Because Ni is sitting at 0 state here, so we will take ground state. But remember class, CO is what? CO is strong ligand. So what is going to happen? Forceful pairing will take place. Forceful pairing. So class, these electrons will be transferred here. In the next step, I'll find that all my 3D levels are fully filled up. 8 were previously there and 2 has moved from 4s. So all are fully filled up. But how many lesions are floating? 4. No vacant orbital in 3D. So now it will move for 4s. Only 1 will be there. So it will move for 4p also. So we get 4 electrons over here. So the configuration, so the hybridization will be sp3. So Ni undergoing sp3, 5 orbitals of 3D, fully filled up, and 4 are being hybridized. So in 4, we'll find that lone pair are being accepted. CO. So class, salient features. Hybridization, what we saw? Hybridization, we saw sp3. Shape will be tetrahedral. Structure, very simple to draw. Ni, 1, 2, 3, 4. CO, and CO. All electrons are paired. So diamagnetic. And if diamagnetic, colorless. Class, 3D orbitals are not taking part. Okay, it is moving for next high energy level. Therefore, it will be also called outer orbital complex. So class, this was an example for coordination number 4. So we have taken both the coordination number 6 as well as 4. We have worked on weak legend as well as we have worked on strong legend. Now class, there is one homework for you. Draw yourself Cr ammonia 6 Cl3, but in this case, remember ammonia acts as weak legend. In other, it acts as strong legend, but in the case of Cr, it acts as weak legend. Class, these were the limitations of valence bond theory. Sometimes they are working as strong legend, sometimes working as weak legend. That we are going to take up in our next session. But for valence bond theory, we have already taken care of coordination number 4 and coordination number 6. This is being given here as assignment. Draw it, but take ammonia as weak legend. Why to draw? Because it's an exception and exceptions are always asked. So try to do it yourself. Now class, will move on. Limitations of valence bond theory. First limitation, it takes into account lot of assumptions as far as strength of reagents are concerned. Class, you have been told that CO, CN, they are acting as strong legend, water and others are acting as weak legend. But why they are acting as strong legend, why others are acting as weak legend, that has not been specified. Point number 2, no information of stability. Why the complexes are highly stable, that also not been told by valence bond theory. Point number 3, why a complex has a particular color. It is also not been explained by valence bond theory. Okay, it does explain that it will be colored or colorless, but it does not explain why a complex has a particular color. And the last point, no explanation of magnetic behavior, though it explained paramagnetic and diamagnetic behavior, but valence bond theory were not able to explain why the low spin or high spin complexes are being formed. So that are the limitations of valence bond theory.